So this section is for petrophysical joint inversion. Let's start just by taking a step back and thinking a little bit about this scenario where you have a petrophysical model. Let's suppose that you build a synthetic model that is very high resolution. You have defined the porosity, the water saturation, shale concentration, the composition for the fluid, and the composition for the minerals at every point. And you have a rock physics model. If you have this and you have a rock physics model, meaning you have very well-defined resistivity model, density model, and so on, you can calculate the physical properties. This would be also using SNUPAR or UT-NUPRO for some of the other properties. You have an effective medium theory for delta P or delta S. And you can do that. You can also, once you have the physical properties, you can generate well logs, like we saw that we did. And this is how rock physics models and well logging simulations work. That is great, it's very accurate. However, that's not how the real world works. The real world works the other way around. You start with well logs, and then you want to get back to a petrophysical model so that you can understand how much oil is there and whether you can get it or not. So we're going to do this opposite. In the previous section, we learned how to go from well logs to physical properties. That was what we did with resistivity. We had a resistivity well log, and we generated an earth model property called resistivity. Now, how do you build a synthetic model? I'm gonna use slides to show you how I built a synthetic model. Very simple. And then we're going to try to get back all the way. So let's assume that we have a model that has shale at the top, shale in the bottom, and some laminated layers in between. I just generated this model randomly using Excel. Just the porosity for the entire rock, for the shale, the water saturation, the shale concentration. These were just using Excel. And we're going to use this as our ground truth. This is what we're going to try to recover at the end. But now we're going to go from here to logs. So starting from here, I literally pasted this in the table view. You can do that, just copy, Control-C, and then Control-V here. Just make sure that you have that in the same order. You can also save this as comma-separated value, which is Excel. Excel can read comma-separated value files. That's how I input this information. I generated some layers first randomly, and then added this. Then I defined two rock classes, one for the shale, one for the laminated part. The laminated rock class is going to have a laminar shale structure, and the shale rock class is going to have a laminar dispersed shale, structure. And for arches, this is the rock classes module. For arches, we're going to use Juhas for the laminated rock class, and we're going to use arches for the shale. We just don't care that much about shale, so we're using arches. That's just an example. Now, if we see this from a compositional palette point of view, this is another one of the modules, probably the most staple module from UTEP Wells, which has evolved along the years. It's a very high resolution view of what you have. And what it's doing is, in the bottom, it tells you which petrophysical layer you're looking at. Then you can look at the specific layer, and tells you what are the components that it has. It tells you what is the matrix, what fraction is the matrix, what fraction is the shale, and so on. Tells you the matrix composition, which we're going to assume that it's completely quartz. Tells you the shale composition, which we're going to assume it's completely illite. We can make this a little more complicated, or a lot more complicated. In a real case, might or might not be more complicated. In many cases, people prefer to just assume it's just one shale component and one matrix component. You can make it as complicated as you want. Tells you, you can modify that here. Tells you everything about the fluid, temperature and pressure. What is the water saturation? What is the salinity? Some calculated fluid properties given the temperature and pressure. These are other properties, other ways of viewing things. And then one of the most important parts is what we have in this panel, which is the structure. It tells you the total porosity, matrix porosity, shale concentration. These four variables are always connected. Then you can infer the laminar factor and the shale factor if you know all these four. But these four are free but connected. And the best way to see them, or what we used to see them, is using the Thomas-Tybert diagram, where you have the total porosity here in the left, shale concentration in the bottom. I'm not going to go into too much detail here, but you can always use the help here for understanding the Thomas-Tybert diagram a little more. One thing that is important is that if you say that this is laminated, this little dot that tells you the relationship between shale concentration, total porosity, matrix porosity, and shale porosity, this little dot should be on top of this line. We have an operation in UTEP wells that is called enforce structure. And if we know that this is laminar, it should match. So we just do that. If we run it, this would force the matrix porosity in this case to match the other things that we have observed. So we would get a better idea of what the shale, matrix porosity should be. Now, how did I do that? I can just use enforce structure and that would do it. Or if you're going to do it not just for that one layer, but for the entire interval, you can use it using the Petrophysical calculator. This is what it looks like. There's a number of, so it performs all these operations which bring properties from the petrophysical composition to physical properties, what we call physical properties, which are things that you can observe indirectly with logs. So we're going to run the enforce structure, then we're going to run the nuclear properties using UTNUPRO. You can use UTNUPRO, you can use SNUPAR sources. We're going to calculate also the water resistivity given the temperature and the salinity. Lastly, we're going to calculate the resistivity, which is going to be, in these cases, notice that for the inverse structure and the arches and similar, which is resistivity, it has this RC button. If you click on that button, you see the windows that we were looking at for that specific model that you're running. Okay. Keep in mind that we must have the right database as well, meaning the right mineral density, the right mineral spectral gamma ray response, and so on. So the way that database looks like is something like this. This is the component editor for solids. You have the name, the formula, and then you have the density, the spectral gamma ray, and you have another number of properties, very similar for fluids. This is where you need to make sure that it's consistent with the field that you're working on. Okay, now, once you have done that, you can generate the petrophysical properties. So I calculated, so from the petrophysical properties that we're using as ground truth, you can use the petrophysical simulator, petrophysical calculator, and calculate those physical properties that I was talking about. So gamma ray, resistivity, density, and neutron porosity. In this case, I'm just going to focus in these four properties. There's more. You can use sonic, you can use photoelectric factor, you can use NMR, but we're going to focus on these four. And then on top of that, you can run the simulation. And these dashed lines are the simulations. They're relatively simple. That's okay. We don't want to get too complicated in this class. Now, we've done the way down. Like I said, what we're really interested in doing is the real world. So going back up. So I've prepared this well, invert synthetic, and it's the same well that you saw in the slides. Now we're gonna go into, what we're trying to do is we're gonna try to recover the properties that we set up just randomly in Excel. Those are, I save them also in an LAS, by the way. I save them from the other well and I load them here. And here we have them in these dashed, dotted lines in black. So those are the ground truth. And then these lines are the actual property in each of these cases. So we're going to focus in this porosity, water saturation, and shale concentration. We're going to try to recover those using the compositional joint inversion module, which if you open it, it looks something like this. It's we've simplified it a lot, and I think for the right reasons. It makes it easier to run, easier to understand. What we have here is the properties that we're trying to match, gamma ray and bulk density. Let's start with these two only. And then the outputs by rock class. So in the laminated rock class, we're going to enforce structure consistency. You can decide to do this or not. And these are just access points to all the other things that are going to be relevant. So the enforce structure, the Petrophysical calculator, these are the databases that I showed you in the slide. This is one way of accessing them. There's many ways. And then you can choose to resample or not for structure. And this is the size of the Latin hypercube sampling grid. 2000 is a good start. It's a good number. You can make it larger or smaller. The way this algorithm works is it generates a number of possibilities given the outputs that you're expecting. These outputs are going to be the mineral composition for the matrix, for the shale, including also, in the shale, we also associate a certain fluid, so it's water. In this case, that we know the hydrocarbon is methane. And the water saturation is an output that you're expecting to get. Porosity, matrix porosity, shale volume. Now, all these are constrained by their prior. The prior is the initial area of exploration, the guesses that you can have. So for example, for porosity, I've already adjusted these ones for given what we know is the truth. In most cases, you should have some information either from previous examples, previous cases, or from core data that gives you an idea of where the porosity should be. For this laminated case, the porosity is between 0.08 and 0.2. It's a Gaussian distribution, so you can make that a little more interesting. You could do something like that. The limits tend to be really what you care about. If we had core data, you could overlay that as a histogram to guide you and make the histogram a little better. We're also working in modules that will do that automatically for you, but for now you can do it using just overlaying one on top of the other. Let's use this one, seems okay. And it's a bit tedious to do it, but you just need to do it once and your entire field has it. So you need to get the porosity for laminated, the porosity for shale. In this case, this is what we're seeing. For shale is smaller, so 0.03 to 0.1. The same thing for all of these things. Really, you're going to care about porosity, water saturation. You don't really care about the minerals. In this case, it's just one. So everything, the mineral composition for the matrix is going to be quartz. That's it. If you have more minerals, then you have to get an idea of what fraction is quartz, what fraction is the other one. The same for the shale. So really the main ones are porosity, water saturation, and shale volume. Shale volume is actually important. And I already adjusted them, but you can adjust them here according to what you want. And then let's just run it. And we're going to try to, actually, before we go into understanding the results of the run, I want to see where we are starting from. We're starting from the physical properties that we already have. So this is the model that we constructed, or that I showed you. I constructed with in the PowerPoint presentation. Then I added some noise to those logs to make it a little more realistic, and then I inverted. This is what those inversions look like for gamma ray, resistivity, density, neutron porosity. Those are the properties that we're looking at. Then now it finished. So these are our inputs, or our possible inputs. Right now, because I'm only using gamma ray and bulk density, is just using this gamma ray and this bulk density. And then we're going to use more. Now, the results that we got from there are this. So this is what the minerals look like. This is our match for porosity, which is not bad, not surprising because we are using gamma ray and density. For shale is also not bad, but for water saturation is not perfect. It's following the right trend, but is not very good. And it's following the right trend because we have the right powers. But to get a better assessment, we really should include the other possible inputs that we have. So let's use resistivity, and let's use neutron porosity. Now, besides this match that we have, so remember the dotted black lines are the ground truth. This is where we should get. The other red lines are the ones that we are getting from the compositional joint inversion. When we run the compositional joint inversion, in most cases, we're not going to have this. This only happens when you have a synthetic case. So how do you know that you're doing a good job? Well, you go here into it's going to open this. I don't know if you noticed, but this track display was open when I said run. And that's the diagnostic plots. And it's how closely can you actually match the properties that you are trying to reproduce. So gamma ray and proposed gamma ray. So this is the in blue here. We have the gamma ray property that we're using as input. So the one I inverted for originally, the one that I showed you in the other slide. And the same thing for density. Then in dashed is what would be the gamma ray if the composition, this composition that our algorithm is proposing was the real one. So if the one it's proposed, you run the calculations just like we did with the synthetic, when we're building the synthetic case, is going to show you here. So the match is near perfect because it's a very simple model. You can see there's some errors down here, and we could investigate why those errors are. But you don't need to have the ground truth to be able to have these diagnostic plots. These are just going to tell you if you're doing a good job or not. And that's okay. So I'm going to close this. Now that we added resistivity and neutron porosity, we should have a good match here and also for water, or better than what we have. Now it's making diagnostic plots, and now because we have more inputs, it's got more plots here, and it's not done. And I see the neutron porosity is not doing very well. I think the output units are not right. I'm going to correct that in a second. I'm just going to let it finish first, and we're going to see how that improves here. It's running UT New Pro in this case. Takes about 30 seconds or something like that to get the final results. Still, you can see these are the results that we got. You can see the water saturation is a lot better. There's some cases where it's not great, but it's okay. We got a better match than we had. And like I was saying, in the properties, no, the units are okay. The units are okay. That could only be in the inversion. So these are there's some cases where it's not doing a great job, but for the most part, is doing a very good match. And we can also see, because it's an Earth model property, we can see the confidence that we have, and you can see it's higher in the places where it's not doing a great job, which is good. You would expect that. You can see neutron porosity, porosity itself should have a lot smaller confidence intervals, and the heat map is more focused. It's easier to get porosity right. That's expected. And this is what we get over here. And it's okay. All right. So this is how you would do a joint inversion and get petrophysical properties. Then you can use these petrophysical properties to calculate hydrocarbon pore volume and really make a better assessment of your field. That's what I have here. I don't know if there's any questions, comments, anything. We've had a number of companies using this algorithm, and in real cases tends to work well. Of course, you need to put some time into making sure that the priors are right, making sure that the model is right. This is, I mean, you would do that with any other approach. But this one also gives you the extra advantage of getting confidence intervals. The uncertainty is propagated from the tool to the log inversion. So from the tool to the physical properties, and then from the physical properties to the petrophysical properties. So getting these confidence intervals is something that we think gives you it can be really important. Can allow you to make a much better evaluation of what you really have. Also, we didn't do it here, but the shale composition is not fixed in this case. The shale composition can vary depending on the priors that you use, depending on the compositions that you use. It may vary slightly or a lot, but in most cases, of course, it's going to vary slightly, but those variations are going to be reflected on the logs and also ultimately in the formation evaluation.